Information and Communication Technology presents educational satellite television programs.
Hello, teacher. Hello, students. Welcome to today's lesson on voltaic cells. We have learned quite a bit about this type of cell already, and there will be several more lessons to come. In our last lesson, we discussed how standard electrode potential is measured. We learned that standard reduction potentials are calculated using standard hydrogen electrodes. We showed this by measuring the cell potential of a zinc-copper voltaic cell using a voltmeter. We also learned how to describe the reactivity of a metal from its position in the activity series, or the electromotive series. In today's lesson, we are going to calculate cell potential. We will decide whether a given redox reaction is spontaneous or not. We will also explain the effect of concentration on a cell. We will look at the dependence of EMF on concentration. Let us begin. If we want to construct a Daniell cell and calculate its potential, we need several materials. We can use a strip of copper, a strip of zinc, and zinc sulfate and copper 2 sulfate, both under standard conditions. We also need saturated potassium chloride solution, 2 100 milliliter beakers, a U-tube, fine sandpaper, and some cotton. We need a piece of copper wire and clips to keep it all together, and a voltmeter to measure the voltage of the cell. To begin, we need to assemble the cell. We fill the U-tube with the saturated potassium chloride and plug each end with cotton. This will help to ensure that no potassium chloride leaks out. It is important to make sure that no air bubbles are trapped in the tube. This device is a salt bridge. We then clean the strip of zinc and the strip of copper with the sandpaper. These will be used as electrodes. Assemble a zinc half cell by putting the zinc sulfate into one of the beakers. Then dip one end of the zinc strip into the zinc sulfate. The same process is repeated with the copper strip and the copper 2 sulfate to make the other half cell. We can see these two half cells at the top of this image. Connect each strip of metal to a copper wire and connect the other end of each wire to the voltmeter. Connect the two half cells using the salt bridge. We can see the finished cell at the bottom of this image. The final step is to read the voltage and note the deflection of the voltmeter needle. Students, let us do an activity. What do you think will happen to the needle of the voltmeter when current begins to flow through the circuit? What does the deflection of the needle indicate? Teacher, please help the students to answer these questions if they are having any difficulty.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. How did you do? The pointer of the voltmeter deflects from the zinc to the copper half cell. This indicates that electrons flow from zinc to copper half cells. Therefore, copper serves as the cathode and zinc serves as the anode. Students, let us do another activity using this redox reaction. Please write the half reactions that are taking place at each half cell. Remember, students, oxidation takes place at the anode and reduction takes place at the cathode.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Welcome back, students. Were you able to write the half reactions for each half cell? Please look at this demonstration to check your answers. This cell represents a spontaneous reaction because it did not need an outside source of energy to react. We can also tell it is spontaneous because the sum of the potentials is positive. It would not be spontaneous if it required the continual application of an outside energy source in order to react. If the sum of the potentials is negative, then we know that the reverse reaction is spontaneous. If the solutions are under standard conditions, the cell potential becomes exactly 1.1 volt. However, if conditions change, such as temperature and concentration, cell potentials can be affected. Let us look at concentration. When electrons move through a wire, they encounter resistance from atoms that are in their pathway. Electromotive force, or EMF, is the driving force that allows electrons to overcome the resistance and continue moving through a circuit. Within a galvanic or voltaic cell, the EMF comes from the redox reaction. It pushes the electrons from the anode to the cathode through the external circuit. Electrons that are on the negative electrode repel each other. They have more potential energy than electrons on the positive electrode. This potential difference causes electrons to flow through the external circuit from the negative terminal, the anode, to the positive terminal, the cathode. The energy of the moving electrons overcomes the resistance in the external circuit. When the electrons flow from the anode to the cathode, product is formed, and the concentration of the reactants decreases. Eventually, the cell reaches equilibrium and there is no transfer of electrons. In this lesson, we learned how to calculate cell potential using a Daniell cell as an example. We learned how to tell if a redox reaction is spontaneous or not. We learned it is only spontaneous if it does not require an outside source of energy. We also learned how concentration affects a cell and the dependence of EMF on concentration. This brings us to the end of our lesson. Until next time, thank you, teacher. Thank you, students.